Hi everybody. This is the final lecture for Chapter 11 in Dynamics, and the section number is 11.5. For those of you who are in class, I'm using the notes that we created in class, but this is a new lecture because the post-processing on the video that we created today failed. So this is a repeat of that information. Probably will go a little bit more quickly because my notes, as you can see, are on the computer screen. The notes are also available to you on our Moodle page, so you can print them off and follow them along, or you can just follow along here. But the lecture for today, 11.5, will be right here in lecture number 4, 11.5. It will have a link instead of a assignment icon as soon as I finish the video, and then the notes that are displaying on my screen that we wrote in class today will be available to you right here. So let's get started. Section 11.5 talks a little bit about two additional coordinate systems. Now, the coordinate system that we've talked about so far is called a Cartesian coordinate system, or we refer to it as a rectilinear system. It's fixed in space, meaning that the x direction is always in one location, the way I have it drawn, horizontally. The y direction is always in one direction, this time vertically, and if we have a z direction, it would come out of the board. Sometimes in physics or in other math classes, you may see that the x, y, z coordinates look like this, where z is up and then x and y actually represent the plane that's perpendicular to the computer screen or the sheet of paper in this case. So in our class, we're just using x, y at this point. We're not extrapolating our conversation into three-dimensional space. So we use x and y where they are in the plane of the board so that we can draw them a little bit easier. The plane of the board, the plane of the piece of paper, the plane of the computer screen. And we will not talk about the z direction coming out. But in general, x is positive to the right, y is positive up. The unit vector associated with the x direction is I, and the unit vector associated with the y direction is j. Now, these are fixed in space, meaning that the origin always remains at the same spot while you're doing a problem, and that x is always horizontal and y is always vertical. However, the two coordinate systems that we'll discuss in section 11.5 represent relative or non-fixed coordinate system. And the first is the tangential normal coordinate system. The second is called radial transverse. And I'll talk about both of them on this video today. So if we take a look at the tangential normal coordinate system, this could be one example of where this system really works. And you always choose a coordinate system based on what is most expedient to get the most amount of information out of with the easiest time for you. One application is when something is moving in a curvilinear fashion. So this is stylized to be, this would be like a road curve, like you're going around a corner as you're driving. And so this vector represents a tangent to that road curve. Now, as you can see, the tangent here has a different direction in a fixed sense than the vector here. But what's going on is that they're always moving tangentially to the curve. So if we take a set of coordinates that are relative in the sense that, I've drawn a circle here, one of the components is tangential to the path of motion, and the other is directed from the point, the instantaneous point or location of the object to the center of curvature, in this case a circle, but it doesn't have to be a circle. Then we still have a mutually orthogonal or perpendicular coordinate system that will completely describe that two-dimensional vector. But now it's easier for us to describe this type of motion because the coordinate system actually moves with the point in question. So some of the things that I've noticed over the years that students get confused over, so I just want to clarify this, is that the letter P represents the point or position of the object. Whereas this letter, which looks very much like a P but is not, is the Greek letter rho, and rho refers to the radius of curvature. In other words, the distance from the center of curvature, whether it's a circle or some other curvilinear shape, to the point itself. So they are not the same. P and rho are not the same. The unit vectors, as you recall in in the Cartesian coordinate system, we used I and j. Here we use E sub t and E sub n. So E sub t is the unit vector in the tangential direction. E sub n is the unit vector in the normal direction. Now it's important to point out these have nothing to do with the natural base or natural logarithms. This E sub t just means unit vector, so it has a strong analog to the idea of I or j, as does E sub n. But a lot of students look at that, and what we're used to looking at is a natural base, and so we think in those terms, but it's not related in any way. It's just a symbol, just like I or j, that indicates the direction of that particular component of the vector. So the important thing to remember is that E sub t and E sub n are perpendicular to one another, even though the location of the point changes and therefore the origin of the coordinate system changes over time. E sub t and E sub n always remain perpendicular to each other. Now this perpendicularity is really important because in two dimensions, if we have a perpendicular coordinate system and we know the components in both of those directions, we can completely describe the vector using essentially the theorem of Pythagoras, which is what TOP stands for. If we use a non-orthogonal coordinate system, we would have to use the law of cosines, which is just more difficult, and we'd also have to, of course, define those angles. So if we just always keep our coordinate systems perpendicular to each other, we don't have that problem mathematically or conceptually. So we talked about the idea of velocity then, and expressing it in terms of expressing acceleration in terms of velocity, and also recognizing that velocity is a vector. Velocity means a magnitude, which we call speed, and the direction of the velocity. So since acceleration is the first derivative of velocity, that means that it can either be caused by a rate of change of velocity, or excuse me, of speed with respect to time, or a rate of change of direction with respect to time. So this is an expression for acceleration in normal tangential components, where the dv dt, or the change in the magnitude of the speed in the tangential direction, and the change in direction, which is expressed by v squared over rho, in the normal direction, sum up to this perpendicular total acceleration of the particle or object. Now, another thing to note is that, and this is what makes tangential normal components really cool, this represents all of the rate of change of the magnitude, and this represents all of the rate of change of the direction. So there's a physical split on this quantity, which is sort of interesting. So anytime that you have something moving in curvilinear motion, going around a curve, you know, NASCARs, anything like that, is using normal and tangential components is quite efficient. Now at that point, we talk about, this was an Euler spiral that I drew in class. The reason I drew it was just to suggest that not all curvilinear problems are circular. And in highway construction, exit ramps are constructed as an Euler spiral, where you start off tight in the curve and the curve loosens up as you go out. So this, of course, would have a different radius of curvature everywhere. Here at the center, the radius of curvature is quite a bit shorter. Here at this point it's longer, and here it gets to almost infinite, where of course infinite radius of curvature would just correspond to a straight line. So this, the less curved an object is, the longer the larger the value of rho will be. So you can use curvilinear motion on Euler spirals or any type of curvilinear motion, as well as circles. Okay, now radial transverse components are more effective for describing oscillations or anything that happens in a periodic kind of way. So the kind of classic example in a lot of dynamics textbooks is some sort of a fixed, or not fixed, but a pivoting arm, like a steel rod, with a collar attached to it, moving through some angle theta. Now, in this case, as the rod spins, the collar will also move unless it's fixed. If it's a free collar, it will move up and down that rod. And for that reason, we describe the motion along the rod and perpendicular to the rod. So we break it down into E sub r components. This would be along the rod, and E sub theta component, which is perpendicular to that. Now that is not, E sub theta is not in any way naturally required to be tangential to the path of motion. It's not tangential to the path of motion in general. There are instances where it is, but it's not to be expected. The other thing is, you notice it's called E sub theta. It's in the theta direction, but it's not theta itself. It's just in the direction of theta. So E sub r is an extension of the rod, and E sub theta, in other words, how much linear distance, or how much linear, what the linear factor is along the rod, and then E sub theta is the factor perpendicular to that direction. So the equations for our radial transverse coordinates are in your textbook on page 694. And they're mathematically a little more complicated than the normal tangential or the rectilinear coordinate systems. So the velocity v as a vector has a component in the radial direction and a component in the theta direction. The component in the radial direction is just r dot, which you remember is the first derivative of r, which is that position or length or distance from O, from the origin, with taking that derivative with respect to time. And then the theta component is r, not r dot, but just r, times theta dot, or the rate of change of this angle with respect to time. Acceleration, r double dot, the second derivative of r with respect to time, minus r, no derivative, times theta dot being the first derivative of theta with respect to time, that number squared. So you take theta dot, square it, multiply it by r, that gets the second term here. First term is the second derivative of r with respect to time. So we have the factor then for the theta direction, the acceleration in the theta direction, which is r theta double dot, second derivative of theta with respect to time. R is just r, that distance, plus 2r dot theta dot. R dot is dr dt, theta dot is theta dt, d theta dt. So it's important to note, and I just note this because I've seen a lot of students confuse this, theta dot squared means theta dot times theta dot. It does not mean theta double dot. So any sort of this word is called a limison. This is like if you take a circle and, like on a, I don't know if you ever guys saw a spirograph. It's kind of a weird toy, but you sort of put a circle outside of a circle and make this increasingly large circular, not really circular, but curvilinear pathway. A limison is defined as the path made by that shape. Or an oscillation lends itself to this sort of analysis. So since you're going to have to do a couple problems, I showed you how I like to break these problems up with a very classical problem. Example 1118 in your book. You're told that theta has a value of 0.15 t squared, where t is time. R is 0.9 minus 0.12 times t squared. And the process for doing this is you first find the first derivative of theta with respect to time. So you differentiate theta once, and then theta double dot, differentiate again with respect to time. Do the same for r. R dot is the first derivative, r double dot is the second derivative. All right, so this problem is set at theta equals 30 degrees. The velocity of theta what is the velocity at 30 degrees and what is acceleration at 30 degrees. Well, the first thing that we need to do is to construct the equations for velocity and acceleration. So we basically take the numbers, or the functionality that we found here, and we plug them into the equation for velocity and acceleration. So when we do that, we come up with these expressions, okay, which can be simplified a little bit. I didn't do it just in the interest of time. Now, when you want to find the value, you would have to plug in the value of t. So what you need to do is to find out at what time t is 30 degrees. So you'd go back to the original equation, and you would plug in, I'm going to say 30 degrees, but I'm going to correct this in just a moment, here, and you would solve for t. This number is actually dimensionless, or in radians. So if you remember studying about radians, a circle has 2 times pi, or 6.28 roughly radians, or 360 degrees. So there's a conversion factor between degrees and radians. So you'd have to change this number into radians by taking and multiplying it by 2 pi radians over 360 degrees. Or you could use an abbreviated form of that. 2 pi divided by 360 could reduce to pi over 180. But in any case, you need to change this into radians after you find the value of t, or before you find the value of t. Then you find the value of t when you're at that position. Plug that value of t into these formulae, and you are set. All right, ladies and gentlemen, well, that's our lecture for section 11.5, and it's actually the last lecture for this chapter, chapter 11. So like I said, that will go here. I've posted some more homework problems that include section 11.5. So there are 3 homework sets, 11.140 to 11.192. These 4 problems are from section 11.5. And our next lecture will be the beginning of chapter 12. So good luck. Get your homework done. If you have questions, please let me know, and I'll help you in any way I can. And I will also not be present on campus on Friday. So the Friday lecture will be recorded in my office like this as well. So I'll talk to you soon. Oh, and yeah, so we'll see you actually, if this is 2019 that you're watching this video. We have a recorded lecture on Friday, and then Monday is Labor Day, so we won't actually meet again until a week from today. Thanks.